So welcome to the last lesson in this section before we move into some exercises in the next section. So this section is about creating and using modules and packages. And modules are fundamental to most programming environments intended for non-trivial programming tasks. They allow programs to be broken up into manageable chunks and provide a mechanism for code reuse across projects. In Python, modules are simply source files ending in .py and located somewhere that Python can find them. In practice, that means the file must be located in the current working directory or folder listed in the sys.path variable. You can add your own folders to this path by specifying them in the Python path environment variable for your system or dynamically at runtime. Although modules provide a useful way of packaging up small amounts of source code for reuse, they are not entirely satisfactory for larger projects such as GUI frameworks or mathematical function libraries. For these, Python provides the concept of a package. A package is essentially a folder full of modules. The only requirement is that the folder should contain a file called __init__.py, which may be empty. To the user, a package looks a lot like a module, and the submodules within the package look like module attributes. So using and creating modules, we access modules using the import keyword, which has many variations in Python. And the most common forms are shown here on this file, which are import is the keyword. And we can import a module as an alias, and we can import several modules with the keyword import. You can also import an object from a module, and you can import that object as an alias. You can import multiple objects from a module, or you can import everything from a module. So the last form, like I said, imports all the visible names from a module into the current namespace. This carries a significant risk of creating naming conflicts with built-in names or names that you have defined or will define locally. It is therefore recommended that you use only the last import form for testing modules at the Python prompt. The small amount of extra typing involved in using the other forms is a small price to pay compared to the confusion that can result from a name clash. The other from forms are much safer because you only import specified names and, if necessary, rename them with an alias. This makes clashes with other local names much less likely. Once we import a module using any of the first three forms, we can access its contents by prefixing the required name with the module name or alias using dot notation. We have already seen an examples of that in the previous section. For example, syspath is an attribute of the sys module. Having said that modules are simply source files, in practice you should observe some do's and don'ts when creating modules. You should avoid top-level code that will be run when the module is imported, except possibly for some initialization of variables that may depend on the local environment. This means that the code you want to reuse should be packaged as a function or a class. It's also common to provide a test function that exercises all the functions and classes in the module. Module names are also traditionally lowercase only. One thing to note that there is a Python style guide known as PEP8 that provides guidance on naming conventions and code layout rules. Its use is not mandatory, but you are strongly recommended to follow it, especially if submitting code for inclusion in the standard library. You can control visibility of the objects within your module in one of two ways. The first is similar to the privacy mechanism used in classes in that we can prefix a name with an underscore. Such names will not be exported when a from X import star style statement is used. The other way to control visibility is to list only the names that you want exported in a top level variable called all. This ensures that only the names we specifically want to be exported will be and is recommended over the underscore method of visibility is important to you. Another note is that one very important gotcha with module is that the syspath list is searched in order. This usually means that any modules we create will be found before the built-in or standard library modules. It is very important that we do not use a standard module name for our own module files, otherwise strange things may happen, and even if you realize that it's your module that's being accessed, other readers are likely to be fooled. And we put most of this into practice by just creating some packages and see how they differ from modules. So using and creating packages, we discovered at the start of this section that a Python package is just a folder with a file called init.py. All other Python files within that folder are modules of the package. Python considers packages as just another type of module, which means that Python packages can contain other packages within them to an arbitrary depth, provided each subpackage also has its own init.py file and that it is a valid package. Note, having just said that a package was defined by having an init.py file, this is not strictly true. The real defining feature of a package is that it has a path attribute, __path __. However, in practice, you don't need to provide that because Python does it for you. So if we created an init.py, all will be well. The init.py file itself is not particularly special. It is just another Python file, and it will be loaded when you import the package. This means that the file can be empty, in which case importing the package simply gives access to the included modules, or it can have Python code within it, like any other module. In particular, it can define an __all list, as described earlier, to control visibility, effectively enabling a package to have private implementation files that are not exported when a client imports the package. A common requirement when you create a package is to have a set of functions or data shared between all the included modules. You can achieve this by putting the shared code into a module file, let's say common.py at the top level of the package, and having all the other modules import common. It will be visible to them as part of the package, but if it is not explicitly included in the __all ___ list, external consumers of the package will not see it. When it comes to using a package, you treat it much like any other module. You have all the usual styles of import available, but the naming scheme is extended by using dot notation to specify which submodules you need from the package hierarchy. When we import a submodule using the dot notation, we effectively define two new names, the package and the module. And we can consider this statement. This code imports the path submodule of the OS package, but it also makes the whole of the OS module visible as well. We can proceed to access OS functions without having a separate import statement for OS itself. One implication of this is that Python automatically executes all of the init.py files that it finds in the imported hierarchy. So in the case of os.path, it executes os.init.py and then path.init.py. On the other hand, if we use aliases after import, like this, only the OS path module is exposed. If we want to use the OS module functions, we will need an explicit import, although only path is exposed. The name pth, both OS and path init.py files will still be run. And the Python standard library contains several packages, including the OS package just mentioned. Others of note include the UI frameworks tkinter and curses, the email package, and the web-focused urlib HTTP and HTML package. So we'll use some of these later in the course. And namespace packages. In Python 3.3, it was introduced a new type of package called namespace package. A namespace package contains a number of portions. A portion is a reference to an object that may or may not have a physical representation and may be located on the network or in a different part of the local file system. Namespace packages do not use the init.py file technique. Rather, they depend on being part of the syspath definition, sys.path definition, used to find modules during imports. Namespace packages are so new that at the current time it is not clear how extensively they will be used. In the short term, we will probably not meet many of them in practice, and the intention is that to a user they should not appear significantly different from the traditional style packages. So knowing how to create and use the standard modules and packages, as well as ones we can create for ourselves, is a great starting point. However, there are many more modules and packages available on the internet, just waiting to be downloaded. Those are called the third-party packages. And many third-party packages are available for Python. Binary distributions of many of these packages, complete with installer programs, are available for most common operating systems. If a binary installer is available either on the package website for Linux users in your package management tool, you should use it because it will be the simplest way of getting things up and running. If a binary package is not available, you need to download it and install the base package. You can find many of these third-party packages in the Python package index, or PyP. They are distributed in a special format that itself requires the installation of a third-party package. The chicken and egg situation often confuses beginners, so this section describes how to set up your own environment such that you can access these third-party packages. PyPy packages come in the form of something called an egg. A Python egg is capable of delivering either a standard Python package or a binary package written in C, or a mix of Python and C code. A little mention on the future of Python packaging. The egg format has some issues, and it is itself being replaced by something called a wheel. This is a part of a wider strategy to rationalize the multiple methods of distributing Python packages and applications. The Python Package Authority is leading this project. Eventually, all the tools needed to both build and install Python packages should be available in a standard Python installation. So with Python 3.5, we already have the pip module included. I'll explain what pip is. Installing an egg requires a tool called pip. Fortunately, installing pip does not require pip. As a version of 3.4 of Python, pip is included in the standard library, which simplifies the process somewhat. If pip is not included in your version of Python, you can install it, Google it, and there follow the instructions for your system. You download the get-pip.py file using, if you Google it, and then you change into that folder and make sure you are connected to the internet, and you run this first command. This will take a few moments and download some stuff from the internet. You will see a few messages, and once pip is installed, you can use it to install a pip package by using this command, pip install a beautiful soup, for example. And this installs the latest version of the specified package. We can uninstall the package just as easily by using this command. And many other options are available to use, and they are described in the pip documentation. Not all packages use pip, and other install options and tools exist as easy install. The package documentation should explain what you need to do. The current state of confusion should resolve itself in the near future, as explained in earlier. And so this is the end of this section also. So I'll just give you a summary of what we have covered. So in this section, we review the core language features of Python. We looked at the interpreter environment, the core data types, and the language control structures and syntax. We also considered how Python can be extended by writing function, classes, module, and packages. And the core data types are Boolean, integer, and floating point numbers, as well as the special non-type. Python also supports several collection types, including strings, bytes, lists, tuples, dictionaries, and sets. The control structures cover all of the structured programming concepts, including sequences, selection, and iteration. Selection is done using if, else, and a conditional expression form. Iteration is supported via two loop constructs, for, which iterates over a collection or iterable object, and while, which is more general and potentially infinite loop. Python also supports exception management via the try, except, finally construct. In addition to a large number of built-in functions, a standard library of modules, Python enables us to extend its capabilities by writing our own functions using the def or lambda keywords. We can also extend the standard data types by creating our own data types using the class keyword and then creating instances of those classes. Functions and classes can be stored in separate files, which constitute Python modules that can be imported into other code, thus facilitating cross-program reuse. Modules can in turn be grouped into packages, which are simply folders containing an init.py file. So that's it for this section, guys, and I will look forward to seeing you in the next section, where we are going to start to look into scripting with Python and see the power of Python there. So see you guys in the next section.